All right. So, so this talk is going to be about supply chain security, more specifically about how we found 0 days in the build pipelines of open source projects. My name is François Proulx, and I'm joined today by my colleague Benoît Côte-Jodoin. We're both supply chain security researchers working for a Montreal-based security startup that is developing an application security posture management product that is meant to help software development teams build secure software and also build it in a more secure way when considering the supply chain threats. So the backstory behind this talk is that when we hear about supply chain, we mostly hear about, oh, it's a bit corrupt. I don't know if we can fix that. It's a bit, sorry about that. So when we hear about supply chain, often we hear about the risk management of known vulnerabilities, so CVEs that go on to, to be the dependencies of your own piece of software. So this area of supply chain is quite mature by now. There are a lot of tools and techniques, especially like SBOM, which is basically creating an inventory of those dependencies that you use in your software. SCA is effectively taking that inventory and identifying the components that are the subject to known vulnerabilities, so CVEs. And it's just getting more and more used at scale. There are a number of products that have been in the market for more than 10 years, such as Sneak, for instance. And overall, the ecosystem around that is quite mature. It's even getting mandated to produce an SBOM by the US government if you want to be a supplier. And also, we've heard about supply chain in the context of various malicious packages being published to package ecosystems such as NPM, PyPy, Docker Hub, and the likes. In that case, a lot of times that is about typo squatting, so kind of publishing malicious packages with just a small typo, where for instance, the famous package in Python called request with just an extra S, for instance, or in the wrong place, is an easy typo to make, and you would be installing the wrong version of a dependency. Dependency confusion is another variant of that. But also, you hear about various aspects of credential stealing to publish malicious packages on behalf of existing trusted packages. And also recently, if you heard about the XZ, LZB, there it was more like social engineering, the long game of convincing the community that someone was an active, well-intended contributor of a popular open source project, like namely that one was a dependency of OpenSSH indirectly through systemd. And at some point, the contributor ended up just sneaking in some backdoor in a very sneaky and complex way. What we're interested in our research is really the build pipeline of those open source packages, because we think it's not as much on most people's radar. So there are a number of initiatives in the past years, such as the OWASP CI/CD Top 10, which covers that aspect, but it really doesn't provide much concrete remediation guidance. It's more like advocacy of the general types of threats, but not much concrete like ways to fix the problems in those build pipelines. There's a lack of tools to find problems like kind of static code analysis in the space at the moment, and even also to inventory the dependencies you may be using at build time and not just as a dependency of your final artifact. There's also suspiciously few CVEs for build time components, namely GitHub Actions. If you look, you'll find that there's not even just shy of 20 CVEs published, which is very suspicious, given that there are tens of thousands of tiny GitHub Actions produced by random people that you may be picking up like a tiny GitHub action that does what you want, but it might have a vulnerability, and this is just kind of outside most people's radar. So we had the intuition that really there should be more to be found in terms of known vulnerabilities in there, and we set out to do that research. Before we move on, I want to set the stage to have a common knowledge about what I mean by supply chain. If you saw my talk last year about supply chain at NorthSec, it was all about the SLSA model, SLSA, which stands for Supply Chain Levels for Software Artifacts. It is an open source threat model published by Google, which is under the Linux Foundation's Open Source Security Foundation. You can find that on salsa.dev. Sorry, it's cropped, the URL. But what's important to know is that this model is kind of capturing a typical software development lifecycle and the main components of it, namely, the developer producing code on their laptop, typically using Git, committing, pushing to, typically GitHub. Hopefully there, he's using some kind of pull request to have a fellow contributor to perform some code review before it gets merged to the main branch. And a lot of times that will trigger some kind of CI/CD, namely GitHub Actions in that case, which will perform various tests, linting and compiling and eventually releasing the final artifact in the case of an open source project, for instance, to NPM, PyPy, Docker Hub again. So when you look at those things, I kind of have little bubbles to kind of give you concrete examples, what that looks like in real life, .github workflows, YAML files would be kind of defining the manifest of GitHub Actions in that case. And in the end, like you are, everyone here is a consumer of those packages in the likes of doing apt install on your Linux machine or pip install or having some kind of NPM dependency in a package JSON of some product you are developing. When we just focus on the build part, there are build time dependencies that don't go on to be part of the final artifact. Those build time dependencies, they are both direct and transitive dependencies, so it can get quite complex. So SLSA namely calls out a number of threats. The use of compromised dependency, where we kind of focus a bit more on the use of compromised build time dependencies, and more generally compromising the build process. So if we open the Pandora's box of the build pipelines of open source projects, in the past year, if you've heard about supply chain, it's most likely in the context of the SolarWinds breach, which is still a very popular networking software that is heavily used in US government departments, so in high, critical departments. And it was a subject of a supply chain breach that indeed focused on the CI/CD of that commercial product. But the same idea applies to open source projects. So the build pipelines overall today are really quite of a mess if you kind of look deeply at it. It's very complex, very hard to analyze the behavior, runtime behavior. The inventory of the build time dependency is just unaccounted for. We have a lack of tools. And you still see a lot of kind of curl pipe bash type of thing where just pulling some scripts and running it like without any kind of cryptographic signature verification. Also, build tools such as compilers, linters, test tools and whatnot were in many cases really not designed with the scenario where you're accepting external contributions from rogue actors and kind of parsing it, and in many cases those tools have little known features that are kind of footgun that lead to remote code execution. So overall, build pipelines, CI/CD, and on all that, we think that they should be treated as carefully as production systems because they end up producing artifacts which go on to be consumed and used in production systems.
So in the process of trying to find these vulnerable repositories, we started mainly manually just finding them, but quickly we realized that there was a fairly common pattern that looks a little something like this in the form of an attack tree. Of course, a lot of open source is on public repos, and some of them will be using GitHub Action. It's sort of a requirements for the things we were looking for. If the project doesn't have any build, well, there's no build to compromise. Then we're specifically looking for a workflow that triggers on an event that is known to be kind of error-prone. It's considered dangerous if you want. In this case, it's an event called pull request target. So this is an event that triggers a workflow on an incoming PR from an untrusted contributor. Then we would be interested in workflows that are using secrets. So if they are authenticating to other systems, that could be interesting. But more often than not, these workflows can omit defining certain permissions. And as such, they receive a default token with a set of default permissions that is usually not necessary. And next, we need some sort of code execution. And there's two ways, mainly we've been seeing how this happens. One is using a script injection. So these workflows can embed user input, say the pull request title, into a script, and then that allows to just execute arbitrary code. Or, as mentioned, build tools that have inherent properties that allow code execution, such as compilers and linters. And at the end of this, you get into a pipeline, and you may start thinking about pivoting or trying to get some impact out of it. So either exfiltratable secrets or maybe try to compromise the artifacts on the repository. But the real attack tree is much more complex than this little scenario. So as we were finding more and more examples, we realized that there was a lot of sort of mitigating factors. There were settings you can enable to be a bit more secure by default. And overall, this problem, I mean, shows kind of the complexity of the problem. And that is only for GitHub Actions. There's numerous build systems that are not covered today. The big problem in our research was that, once we get code execution, we find these vulnerable workflows, then we have the problem of trying to evaluate the impact of it. So if we compromise a GitHub Actions, for instance, it will be used in other build pipelines that will use other build pipelines. So trying to find these issues recursively was a bit of a challenge. This is a sample vulnerable workflow that is a bit cropped, unfortunately. But as mentioned, there's numerous problems in this that we were looking for. In the case of a PON request, there's mainly three things we're looking for. So the pull request target event, which is often misused. Then we look for this ref down here, which will actually pull down the pull request changes. So these are sort of untrusted external contributor code changes, so they can be any files modified in the repository. And then what we don't really see at the bottom is you need some sort of command or injection that will trigger the remote code execution. So in this case, at the bottom, there's a call to make. So if you run make on untrusted changes, it will load the make file. It will run any command you want. That's not great. Or you may be embedding user input into the bash script that is executed down there. And there's another set of problems in here, like we mentioned untracked supply chain dependencies, so you can use containers. And there's also the permissions that the workflow has. So in this case, it's given a fairly privileged access token. It doesn't define permissions, so it defaults to read-write access on the repository. So these set of problems were very common, and we set out to try to find these. So to make this happen, we created a project called Package Supply. And the goal of this project was to analyze the CI workflows of common open source packages that are not really used or tracked in SBOMs, they don't have really CVEs attached, but they have a really critical role, such as GitHub Actions or Terraform modules, which you give generally your most powerful credentials to. The process of analyzing each packages is often the same. We try to clone the source repository if we can find it. Then we will parse any CI workflows that we find. We'll run some static analysis security tools to try to get some findings out of there. And then at the end of this process, we end up with sort of a build inventory. So all the build components that we saw in this project, this allows us to sort of recursively crawl like the build package graph of these projects. And to kickstart this process, we scraped a large number of repos just to showcase that this approach really scaled. And in order to analyze it, we put everything into BigQuery. And this really allowed us to do like static analysis using SQL, but it's really efficient. You can test heuristic really quickly rather than running a tool 350 times every time you want to add more to it. And the other analysis tool we use is Neo4j, so it is a graph database. And this allows us to, once we find like a vulnerable package, we can sort of evaluate the impact of it in the ecosystem. This is a sample of the current data that we have and some of the heuristic that we're using. So on the left, you see the sort of input packages. And then we see in the middle that roughly half of the repositories that we found had GitHub Actions. And then, interestingly, most or all of them don't define permissions. So depending on where this workflow is, it may inherit more permissions than it needs. We have the trigger on risky events. So this is the pull request target event. There are other events we're looking for in these workflows that are commonly misused. And then at the bottom, a bit lower in incidence rates is the injections and the untrusted code checkout. So once you start putting all of these heuristics together, you get a fairly high signal towards vulnerable open source packages. And once we find one, we put it in BigQuery to look at the entire build graph. And these are fairly normal and expected. These build graphs get large really, really quickly. And in this case, we're able to see that, say, a package that has a command injection then affects, a very large number of dependencies. And so this is getting really interesting as a project. So we started looking at individual repos and then try to find how these vulnerabilities in build projects could affect other things. And we found a number of things that François will be discussing.
Thank you. So yeah, with all that, that allowed us to indeed find 0 days in the build pipelines of open source project and perform like responsible disclosure. Namely, at the beginning, we were focusing our attention quite a bit on Terraform providers and modules because we thought they were simply, it was an ecosystem that was simply forgotten by most people that typically would be looking at NPM and PyPy again. So yeah, we did find a number of those problems, namely in the category of pull request, those kind of build tools that have little known features that are dangerous. And we started to see patterns emerge, and we coined the term living off the pipeline, as a nod to living off the land, which is a classic type of post-exploitation or exploitation kind of name that we see in MITRE and things like that, but applied to the build pipeline here. So we've created this project, Living Off the Pipeline, to inventory all those tools, such as Gunplate, which you'll see in just a moment. And there are also injections, and this is just a small sample. We have many more yet to be disclosed. So if we just focus on this living off the pipeline, sorry, the URL is literally corrupt at the top, but you can find it, like Google it and find it on GitHub. So this is an example of Gunplate. So Gunplate has a little known feature. So first, it's a kind of a template engine in the Go language. It has this feature which you can configure it not just with a command line parameter, but also with a config file, namely .gunplate YAML, which if you're submitting a pull request, you can just add that file if it was not present, and read the documentation and figure out that there's this interesting feature called post-exec, which you can just specify any arbitrary command, and then you get remote code execution in the context of a build pipeline. So I'll do a demo of something. This is directly inspired by one of those responsible disclosure we've done on a Terraform module that was used, downloaded hundreds of millions of times like very popular, not to name it like the second most popular on the Terraform registry last year. So before I move on to the actual demo, just explain a little bit. The Terraform registry has both providers and modules. Modules can have dependencies themselves. Modules and providers, effectively, when you want to publish them, it's literally no more than a GitHub repo, which every time you tag, it will automatically publish to the registry. So it's as easy as that. If you have the ability to tag, you are publishing. So if we look at the Terraform module B in that case, it's on GitHub. It's using GitHub Actions. It's using various build tools, namely Gunplate, which I just told you a moment ago. And GitHub Action has dependencies itself. So the attacker comes in, forks the repo, submits a pull request, pretending to be some kind of typo fix, but really what it's adding is this .gunplate YAML, which contains the command. The other way that could be exploited, which we've seen in the wild, is malicious Git branch name. Any Git ref tag branch is at the maximum 255 characters, because really it needs to be a valid Unix file name. So anything that can fit as a valid Unix file name, and you'd be surprised what is a valid Unix file name in terms of the characters that are allowed. It's more than enough to do bash or JavaScript injection. So seen that in the past, and you can find examples in our stuff. So basically it triggers the test, which one of those has a vulnerable GitHub action, and ultimately that allows the attacker to backdoor the Terraform module B, which is a dependency of module A. So you don't even know, like you use module A, you don't necessarily notice it has module B, but suddenly it got backdoored. So in the end, the outcome is that the attacker is able to exfiltrate the OpenID Connect credential in Terraform Cloud, which allows to completely circumvent Terraform and just attack the cloud directly with the high power, token. So the demo. All right. So So basically, see Terraform registry. There's one module, version 1, which has a dependency, module B. All right. So module B has this dependency, version 109. And if we look at the GitHub repo of that module, we can see the legitimate version 109 at the moment. Someone is using Terraform, in that case Terraform Cloud, but doesn't have to be. They're going to be running like the plan applying. Meanwhile, the attacker is setting up its attack. It has some kind of honeypot to collect the tokens at the end of the attack. So everything is scripted. So what it does, it's going to fork the Terraform module repo, submit the PR that has the Gunplate payload. And if we just zoom past a bit, so we'll look at that PR. That PR indeed contains this malicious file. And if we just wait a few seconds, GitHub action is going to run. In that case, just formatting the README, which is a real-world example we've seen that was vulnerable to that. And at that moment, the attacker is able to actually clean up after covered error traces. The cleanup script is basically doing a git force push to remove the suspicious file, closing the PR, and there's nothing suspicious at that moment. Even if we inspect the main branch, we will not see the backdoor. We can see now that the rogue version has been published under the token that was from GitHub Action. So now there's a backdoored version, but if we audit the repo, we will not see the backdoor. It's not present. There's nothing new, literally like no diff in the main branch. But if we pay attention to the latest release, we see that the tag is pointing to a dangling commit, like an orphan commit that is not part of the repo. So the backdoor is there. And meanwhile, someone is using Terraform, and literally, like from 1 minute to the other, they don't know that there was no backdoor, and now there is a backdoor that is pulled because it will refresh the module B automatically. And from the perspective of the user, nothing is completely silent. There's nothing, even doesn't show up in the logs. Like if you look at the logs, it can be completely silent. Meanwhile, the token to Google Cloud in that case has been exfiltrated. So what can we do about that? I would say, go back to that SALSA model, threat model, your overall software development lifecycle to consider supply chain attacks, kind of understand your build dependencies and whatnot. Overall, inventory and potentially reduce your number of dependencies, pick better dependencies, better maintain, more secure if possible. But at least kind of be aware of what's out there and to be just proactive. Also, least privilege, just apply the common least privilege principle. Like again, those default permissions in GitHub Action, there's a way to kind of configure, like to lower the default permissions, for instance, or specify lower permissions explicitly. Also running some kind of static code analysis tools on your build pipelines. And that is a good segue to an open source tool which we've released about a month ago called Proulx. Proulx is an open source security scanner focusing today on GitHub Actions and GitLab, but we have plans to expand it. We're looking for feedback from you if you have specific use cases you'd like it to apply today. You can point it to a GitHub organization or just a Git repo, and it will scan very efficiently. Namely, you can point it to orgs that have hundreds or thousands of repos. It will return results within literally less than a few minutes. So it's just as easy and lightweight to run it against your own build pipelines, build it inside of just as kind of security check of your own pipelines. So we use it as part of this whole package supply project, and go find it on GitHub, and try and possibly contribute. Again, just feedback is a good contribution. So what it looks like, you install Proulx, you can run it as a Docker container too. You give it a read-only token to repos, and it will return like the types of vulnerabilities we've discussed so far. So there's also the Messi Proulx project on GitHub, which is really a capture the flag thing. It was designed to kind of test our tool. So you can give it a try. Literally, you can exploit those workflows. There are about 20 or so flags. So far, no one has got them all. Even like the red team at Mendiant, they were unable to find the hardest ones. So come talk to me. I can give you some hints. Overall, the security of build pipelines is really complex. It's an area that's still under most people's radar. Our research is really starting just to scratch the surface of that problem. Our statistical analysis, namely in Proulx, is still quite shallow, simplistic, but it's already finding very important problems. Again, CI/CD should be treated just as seriously as production systems. And we've demonstrated to you some real-world scenarios that are, in some cases, very easy to exploit. Just go try and Messi Proulx. The first challenge, you should be able to figure it out within just a few minutes at most, hopefully. And Proulx, you can give it a try, and that's it. There are a number of articles we've published in the past year about this topic, discussing in more details those responsible disclosure and the gotcha behind those, and the projects I've mentioned. In this case, you can see the URL because it's not cropped. Thank you.